I welcome you all to this introductory lecture on basic circuit theories. So today's session is based on the circuit theory of electrical engineering. So let us start with the topic study about the circuit and network. Basically, what is the difference between the circuit and network? The various circuit elements available in electrical circuit theory: resistance, inductance and capacitance, the concept of voltage and current and their notations, then various definitions or terms used in circuit analysis like the voltage source, current source and the dependent sources, independent sources, then terminal relation of the current and voltage sources and resistance, inductors and capacitors. So we will see that what is the voltage and current relationship for the current for this resistor, inductor and capacitor. These are very elementary topics of the circuit theory, but one should know the concepts. How can we derive these relationships? Now we will also discuss about the calculate this current, voltage, power, resistance for any electric circuit using Kirchhoff current law, Kirchhoff voltage law, and there are so many methods which are available in circuit for solving the electrical circuit. First of all, we will discuss that what is electrical circuit and electrical network. One question must be arising in your mind, that is there any difference between the circuit and network, or both are same? Yes, my dear friend, in practice we say sometimes circuit and sometimes network. Sometimes we say this is a circuit, sometimes we say this is a network. But is there any difference between these two? Yes. Let us understand first what is electrical network. Electrical network is any possible interconnection of electrical circuit elements or components. So what is these electrical elements and components? Yes, this R, L, C, resistance, inductance and capacitance, or resistor, inductor, capacitor. These are the circuit element. These are connected with the source. This is the voltage source here. So any possible interconnection like resistance, inductance and capacitance, they may be interconnected in any manner with the source. Then we can say this is forming a network. Here resistance, inductance and capacitor, these are connected in this manner, in this T manner. Here we call it as a network. This is also the possible interconnection between the circuit elements. So we can call it as a network. Basically, when we talk about the electrical circuit means we just understand about the closed path. When we give the definition of electrical circuit, we can say an electrical circuit is a closed energized network. Where is the circuit between these two? Yes, this is circuit because this is forming a closed energized network. See, if the voltage source is active here, this is the plus minus, and the current will flow through this path, that means it is making a closed energized network. That means this is forming an electrical circuit. But here this is not a closed path, so this is not forming any circuit. That means this is a network but not circuit, and this is a network and we can call it as a circuit also because this is a closed energized network. So all the circuits are network. Okay. Now let us come to the second slide of this. We will discuss about the circuit elements. In electrical, generally the basic circuit elements are the resistance, inductance and capacitance. Here this is the voltage source, this is the independent voltage source, this is the dependent voltage source, this is also type of the current sources. So any individual circuit component with two terminals like resistance, inductance, capacitance, they are having 1, 2, these two terminal, here also two terminals. Basically, when we can divide the circuit elements in two parts, the active elements and passive elements. So what are these active elements? When we talk about the active elements, we can say which delivers the energy. This is a circuit or this is a network. This is voltage source connected across this R and C. This is delivering energy to this elements R and C. This voltage source is a active element, and What about R and C? These are called passive elements. The elements which absorbs energy are called passive element. Resistance, inductance and capacitance is having the property of absorbing the energy, and this is a source, current source, voltage source, they deliver energy. So, they are called active elements. You must be aware about this, the Ohm's law. The Ohm's law is used to define the voltage current relationship for the resistance. Basically, first of all, what is resistance? Resistance which restricts the flow of electric current through any material. Basically, it opposes the flow of current. Here, when we give the relationship for the resistance which is defined by the Ohm's law, R equal to V by I, or we can say if we apply the voltage across this resistance, then the current will flow through this, and this current will be proportional to the applied voltage. That means V is proportional to the I, or I is proportional to the V. Now, what is the power absorbed by a resistance? Generally, the power absorbed by any resistance is given by the P is equal to V into I, the voltage into current. So, here this is the power relationship in the case of the resistance. I into R, I, we are putting the value of V from the Ohm's law. So, I square R watt. This is the power absorbed by any resistance is given by I square R. Now, the energy is absorbed, energy lost in resistance generally in the form of heat. So, this heat loss or this energy is given by this relationship. From the power we can derive the relationship for the energy also, and W is equal to P into T, you know, or we can say P is equal to dW by dt, rate of change of energy is equal to, this is power. So, we can say the energy W is equal to time integration 0 to T P dt. So, this change in power with time 0 to T, right, we can put the value of P. So, W is equal to P into T. So, I square R T, we have derived the relation for the power. So, the energy is given by V square by R T. So, now let us see the inductance. What is inductance? Inductance is a property of the material by virtue of which it opposes any change of magnitude and direction of electric current passing through the conductor. Unit of inductance is Henry. Generally, it is just like the resistance which is represented by the unit ohm, the inductance is represented by Henry. So, here this is the symbol of the inductance. Now, we will derive the basic relationship in the case of the inductance. In the case of inductance, we can say, suppose this is the material in the coil form which is having some inductance, we can say this is inductance is L here. When we apply the current, suppose the current is passing through this inductor, then what will happen? The flux will link from the Oersted rule. When the current is passing through, the magnetic field will be, the flux will link with the coil, the turns of the coil. Psi is proportional to I, where the psi is the flux linkage, which can be denoted by N phi. N is the number of turns in this coil, and the phi is the flux associated with the one coil, one turn. So, here the flux linkage is given by Li. L is the constant of proportionality here. When we remove this proportional sign, then we can put it equal, and L is the constant of proportionality, and which is constant. You know, V is equal to d psi by dt. Here, this is from the Faraday's law. According to Faraday's law, the voltage EMF induced is equal to the rate of change of flux linkage. So, here from the Faraday's law, we derive this relationship. Now, we know the value of psi from here. We can put the value here. This is Li. That means, we are finding this relationship V is equal to L di by dt. When we put here Li, L is constant. So, we can take it outside. Then we can write it L di by dt. This is the voltage current relationship in the case of inductance. See, V voltage, I current. So, when we differentiate this current, di by dt multiplied by L, it gives the voltage across the inductor. Similarly, we can get the value of I from this relation. It at any time t, the current through the inductor can be given by 1 upon L integration of V dt. When you will integrate this, you will get I, this L is here 1 upon L, then you will get 1 upon L integration of V dt. In time form, when we write this, we can say here 0 to T V dt, and this is the initial value of the current, because the current is equal to current plus current at any time t. This is showing the current, and at initial time, so this is the initial value of the current. In the case of inductance, you can also give the relationship for the power and the energy. So, the power is V into I. You just put the value of V. V is equal to L di by dt multiplied by I. This is the power in case of inductance. Similarly, you can give the relationship for the energy also. You will get, when you put this value here, P, and integrate it, half Li square. This is the energy absorbed by this inductor. That means this is the passive element, inductor, which absorbs energy. Now let us see the capacitance. What is capacitor? This is a capacitor. The two plates are here, and which is separated by the any dielectric medium, which may be air. In this case, we are applying the voltage V across these two terminals. When we apply the voltage V across this terminal, that means these plates are energized and the charge is stored here. This plate is positive and this is making this plate is negative. When we talk about the capacitance, it is the capacity of an element to store electric charge within it. A capacitor stores electric energy field. Quantitatively, capacitor is a measure of charge per unit voltage that can be stored in an element. The unit of capacitance is farad. Here, when we apply the voltage V across this, the charge accumulated across the capacitor plate is proportional to the applied voltage, which is given by this relationship Q is proportional to V. So here Q is equal to, when we remove this sign, proportional sign here, so we will put here C. This is the constant of proportionality, which is called capacitance. Now how can we give the relationship for the current and voltage in the case of capacitor, just like in the case of resistance and the inductance? So this is the basic relationship for in the case of the capacitor. Just like in the case of inductor, the basic relationship was Xi is equal to Li, and the case of the capacitor, we can write I equal to dq by dt. This is the current relationship. You know this thing, rate of change of charge. This is dq by dt is equal to I. We know the value of Q from here. Q is equal to C into V. Put the value here. C is the constant of proportionality. We can take it outside. So here I equal to C dV by dt. Relationship between the current and voltage. The current is given by the C and the differentiation of the change in voltage with time, dV by dt. So I is equal to C dV by dt. This is the relation for the current and voltage. From this relation you can give you can also relate the voltage and current. You can give the relationship for the voltage in terms of current. Here this is the current in terms of voltage. I is equal to C dV by dt. We have already derived this. We want to find out, basically we want to find out the voltage. How can we express the voltage in terms of current now? From here dV is equal to 1 upon C I dt, we can write it, or we can say V equal to what? Integration of dV from time 0 to t. We are putting the value of this dV from this relation, and we are getting the relation 1 upon C 0 to t I dt. V equal to 1 upon C integration of I dt. When we talk about this is the voltage V is having the two component. This is the initial voltage and the final voltage. The V0 shows the initial voltage of the capacitor and Vt shows the final voltage across the capacitor plate. So here this is 1 upon C integration of I dt. This is the relationship for the voltage current relationship in the case of the capacitor. Now what is the power absorbed by a capacitor? P is equal to Vi. The same relationship we are using for this. Take it as a small v small I, that means this is the instantaneous value of the voltage and current. V, put the value of I here, I is equal to C dV by dt. So this is the power. From this power relationship you can also derive the relationship for the energy. Just like W is equal to, you can say integration of P dt. Put the value of P here. When you are putting the value of P here and just solve this, you will get half CV square. So this is the energy absorbed by this capacitor, half CV square joule. So we can relate the voltage and current relationship here at a one glance. So here you can say this R L C, and the voltage relationship, current relationship, and the power relationship for each case. For in the case of R, V is equal to Ri, I equal to V by R, P is equal to I square R. In the case of inductor, you can say, which is given the unit of inductance is the Henry here. You can give the V is equal to L di by dt. Similarly, you can give the relationship for the I also, 1 upon L integration of V dt, and P is equal to L di by dt, Li di by dt. This is in the case of inductor. Similarly, in the case of capacitor, P is equal to C V dV by dt, just which is obtained from P is equal to I into V, and put the value of I here, you will get this relationship. In the case of C, V equal to 1 upon C integration of IDT. So before solving any question which is having these elements resistance, inductance and capacitance, one should know what are the relationships for the current and voltage for these elements. Before applying these relationships, you can't solve any question or you can't get the value of these elements and you can't calculate the value of voltage and current in any circuit. So these are the basic relationship, voltage current relationship. Now let us see one example based on these relationships. The current and the voltage profile of an element versus time has been shown in the figure. What is the element and find its value? Here the relationship between the current and time is given, voltage and time is given, and you have to find out what is the value of the element for which these relationships are given. So this is the inductor, we can say, you know, for the inductor V is equal to L di by dt. Here you can say the initial value of the voltage is 2 volt. See, this is the time varying. When the time is changing from 0 to 5, this voltage is reaching from 0 to 2. So the initial, you can say this value is 2 volt, and here this is the time is reaching from 0 to 5 and the current is from 0 to 1 ampere. So the change in current with time, you can say di by dt can be given as 1 upon 5 multiplied 10 to the power minus 3. You will get this 0.2 into 10 to the power 3 ampere per second. Just use the relationship V is equal to L di by dt. So L equal to V upon di by dt. Put the value, you will get the value of the inductance. So here this is the 10 millihenry. This figure exhibits the voltage time profile of a source to charge a capacitor of 50 microfarad. The value of the capacitor is given in the problem. The capacitor is of 50 microfarad. What is the charging current? And the time voltage relationship is given, and the value which is asked is here the charging current. So how do we get this? The value of current. As the voltage is given here, just use the relationship, voltage current relationship for the case of the capacitor. I is equal to C dV by dt. You should know this relationship. Find the value of dV by dt from this curve. The change in voltage with time is given. This is the dV by dt. Here you can see from the voltage is changing from 0 to 20 volt. So you are putting the value 20 here. Dt, time is changing from 0 to 10. So you are putting the 10 minus 0, you are putting the value 10 here. So here you are getting the 2, or you can say this is the 2 into 10 to the power 3 volt per millisecond, because the time is given in millisecond here. The charging current is C multiplied by this. You will get the value. Try to understand this relationship, the use of this relationship which we are using in the case of the capacitor, where the curve for the voltage and the time is given. Now let us discuss about the energy sources. In electrical circuit, when we talk about the energy sources, there are two kinds of sources, the current source and the voltage source. We further divided into the two parts. The current source is the dependent current source and the independent current source. Similarly, the voltage source is also the dependent voltage source and the independent voltage source. Now, how do we differentiate and how can we denote these sources? This is the independent voltage source. This is the dependent voltage source. See, when we talk about the voltage source, here the sign is plus minus inside the circle, plus minus. This is the dependent voltage source. This is the independent current source. This is the dependent current source. Alternating sources, the sources with periodic waveforms. We can use these sources when we solve the circuit problem. This is the voltage source, both are the current source. One is independent, one is dependent. Here one is independent source, one is dependent source. What are the dependent sources and what are the independent sources? In independent sources, they have the constant value of the voltage and current. That means which delivers the constant energy. If we talk about the voltage source, that means it is delivering the constant voltage irrespective of the current through any circuit. And similarly, when we talk about a dependent voltage source, that means its value may change according to the circuit element. That means its value is depending upon any circuit variable. You will understand it when we solve the problem, and then I will also explain this. How can you differentiate between these sources? First of all, see the voltage source. When we define the voltage source, any hypothetical generator which is giving the constant supply of the voltage is called as voltage source, irrespective of whatever the current through the load. The current may change, but voltage will always remain constant. This is called voltage source. A voltage source is shown like this. E, the value is given here. Across this load, we are getting that voltage Vt. This is the curve for the change in voltage with time. This is the time varying voltage source. At time t1, the value of the source is E1, and with time t2, the value of the voltage is E2. That means the constant voltage supply is changing with at any instant the value of the voltage was this, and other instance the value of the voltage is this. So this is the time varying voltage source. Here this is the time invariant voltage source which is having the constant value. That means suppose it is the source is of the 10 volt, it will deliver the constant voltage of 10 volt whatever the current through this. This is the constant. The current is changing from 0 to some ampere, but the voltage is always remain. Suppose this is the 5 ampere. So, the voltage is constant. There are two types of sources, the practical source and the ideal source. When we talk about the ideal voltage source, the ideal voltage source, that means suppose if we are taking the voltage source of 5 volt, it will deliver the 5 volt across the load terminal. This is ideal case. But when we talk about the practical voltage source, what will happen? Suppose we are taking the voltage source of 5 volt, it will give 4.8 volt across the load terminal. That means this is not ideal, this is a practical. A voltage source is here which is having some resistance, some internal resistance. Its internal resistance is shown by this R. What is the voltage across these two terminal? Suppose we connect the load here across this terminal and get the voltage across this, we will see if this voltage source is ideal, that means this resistance should be 0. That means the whole voltage, whatever voltage we are applying here across the load terminal, this should appear across the load terminal. We will get the E voltage across the load terminal. But if it is having some internal resistance, suppose of 0.2 ohm, then the voltage will drop through this. For this curve we are saying this is suppose this is the 5 volt. In this case this has become the 4.8 volt, that means the 0.2 volt drop here. This is the example of the practical voltage source which is having some internal resistance. Let us see the current source. This is a notation for the current source, arrow inside the circle. Sometimes in some books you will find this kind of notation for the current source. This is the ideal current source. When we connect the load here, this will deliver a current of I to this load. The time varying current source, we can say at any time t, this is the current, but it is giving the constant supply, constant current irrespective of the voltage. Voltage may change, but the source is giving the constant current. At any one time t1, this is giving current I1, time t2 it is giving current I2. This is a time varying current source. Now let us see the practical current source. The current source which is not ideal, that means suppose we are taking the current source of 5 ampere, it should deliver the current of 5 ampere. That means this is the ideal current source. But if we say the practical current source, that means if we are using the 5 ampere current source, it is not giving the complete 5 ampere across the load terminal, and suppose this is giving the 4.8 ampere, that means the 0.2 ampere has lost. This is called the practical current source. So how do we represent this case? Ideal case and the practical case. This is the representation of this, the practical current source. If we take this only this part, that this is the ideal case. Across the load, suppose we connect any load here across this load terminal, this will deliver the current I suppose. But we want to show some drop, that means suppose we are not getting here the complete 5 ampere, here we are getting the 4.8 ampere. That means there is something here which where the current is going, which is shown by the internal resistance of the current source. And this internal resistance of the current source can be shown only in the parallel of this. Suppose it is delivering the current of 5 ampere. The whole 5 ampere is not reaching here across the load terminal. Some current is passing through the resistance. This 0.2 ampere current is passing through the resistance. That means according to this internal resistance of the current source, some current will passing through this, and we will get less current across the load terminal. This is the practical current source example of this, which is not ideal. Suppose we connect voltage source of I ampere across the load terminal, that means it will deliver the constant supply, the constant current. That means this is the ideal case. But if there is some drop, we are not getting the complete current, then this is the practical case, like just shown by this figure. So this is the second case due to the internal resistance of the current source. Suppose we want to make this current source ideal, then what should be the value of this resistance? It should be infinite. If this is infinite, that means no current will pass through this. Infinite resistance means open circuit, that means no current will pass through this. Then the whole current will flow through the load terminals. No current will pass through this part. Ideal case, this should be infinity. Now what is a source transformation? We have studied the current source and we have studied the voltage source. What is the ideal voltage source, ideal current source, practical current source, practical voltage source. Now there is one more thing which comes in practice when we solve the problems of the electrical circuits. How do we transform the current source into the voltage source and the voltage source into the current source? And this technique by which we transform the electrical current source to the electrical voltage source is called a source transformation. This is the practical voltage source. This voltage source can be transformed into the current source, equivalent current source. That means in this case any resistance R is connected across the load terminal, and we are getting the, when we solve this and we are getting the value of I ampere current is flowing through this load terminal or resistance is connected here. Suppose 5 ampere current is flowing through this. When we connect the same resistance here, then we will find if these two circuits are equivalent to each other, then the same 5 ampere current will flow through this. Now the question is, how can we transform this voltage source into the current source? What will be the value of this I and R when we transform this circuit to this circuit? This is called the source transformation technique. That means the voltage source in series with the resistance, but when we convert it into the current source, then we will say the current source in parallel with the resistance. This is the current source. Now what will be the value of this I? This I is equal to V into R. Suppose this is of 5 volt. So 5 multiplied by this R is equal to the value of this current. This parallel resistance, this will be the same as the resistance in series. Whatever the value of this resistance, the same value will be remain here. If you put this formula here and if you convert it like this, that means you are making these two circuits equivalent to each other. That means here this is the current source, this is the voltage source. That means this is called a source transformation technique, where you are converting the voltage source into the current source. Now let us take one example. Here we are changing this voltage source into the current source. How? This is the voltage source of 100 volt. We want to change it into the current source. That means what will be the value of I? I is equal to V by R. That means V is 100, 100 by 10 is equal to 10. That means the value of the current source is here 10 ampere, and the parallel resistance will be same as in the case of the voltage source. This 10 will remain 10. You will find that both circuits are equivalent to each other. That means we are converting the voltage source into the current source. If you connect any resistance or any load here, you will find the voltage and current. Whatever voltage and current will flow in this case, the same voltage and current will flow in this case if you connect the same load here. That means two circuits are equivalent to each other. So this is the source transformation technique which we use very often in case of when we solve the problems of the circuit. Now one of the very basic things is the division of the currents in parallel circuit. Basically you should know the formula, your shortcut formula for this. Suppose the current is flowing and it is dividing into two parts, R1 and R2. Then what will be the value of the current through the first resistance and what will be the value of the current through the second resistance? Basically that you should know the shortcut technique. Suppose the I current is passing through this, what is the value of I1? So I1 is equal to the total current I multiplied by this resistance divided by this plus this resistance. This current will flow through this R1 resistance. Similarly, if you want to find out the current through this R2, then you will say the current through the R2, I2 is equal to total current I multiplied by the first resistance divided by first resistance plus second resistance. So here we can derive this thing. V is equal to, suppose the equivalent voltage, when we supply the current I through this network, this two resistance R1 and R2 parallel combination of this, then we can say the total voltage across this is suppose Vp. You know Vp is equal to IRP, we can write, where Rp is the equivalent resistance of this, both are parallel. So you can say the equivalent resistance is R1 R2 divided by R1 plus R2. You can write it like this. What is the current? I1. I1 is equal to the voltage across this, both are parallel, the voltage will appear same. So here this is the Vp divided by R1. Put the value of Vp from first, then you will get this, and that means you are getting I1 is equal to I multiplied by R2 divided by R1 plus R2. This is the shortcut formula for this kind of problem. That means I current is dividing into the two part I1 and I2 due to the two resistances R1 and R2. Then the current to the first part I1 is equal to the total current I multiplied by the second resistance divided by first plus second resistance. Similarly, in the case of the current through this I2, we can derive the formula for this current I2. This I2 is equal to I multiplied by resistance, first resistance divided by first resistance plus second resistance. In the same manner, we are deriving this. Or we can say I2 is equal to total current I minus current in the first element R1, I1. Now the voltage division in series circuit. We have studied the current division. Now we will see what is the voltage division. In the case of the voltage division, suppose the two resistance R1 and R2 are connected in series and we are applying the voltage source across this. Then this voltage will be divided into the two parts, V1 and V2. What will be the value of this V1 and what will be the value of this V2? That means the voltage across R1 and the voltage across R2. We can find this voltage like I equal to, from this circuit you will find I equal to E divided by R1 plus R2. This relationship can be obtained from the Kirchhoff voltage law. Then voltage across R1 is given by V equal to V1 is equal to I R1 I series, the current will same through I1, this R1 and R2. So you can put it here. You can remember this shortcut formula for this, the voltage division in the series circuit. Suppose the current is flowing through this, then the voltage across R1 is equal to the total voltage multiplied by R2 divided by R1 plus R2. If you want to find out the current through this part, that means this is the voltage multiplied by this resistance divided by first resistance plus second resistance. This is the voltage across the second terminal. Now, the two other basic laws in the case of the circuit theory is the Kirchhoff's current law and the Kirchhoff voltage law, which are the preliminary law in that which one should know to find the value of the current and voltage. These laws are known as Kirchhoff's law. The Kirchhoff's current law, which gives the relation for the current at any junction is equal to 0, and the second law is the Kirchhoff voltage law, which relates the voltage in all the branches of the circuit. The summation of EMF plus summation of voltage drop is equal to 0. This is the second law of the Kirchhoff. And before studying the Kirchhoff's current law and Kirchhoff voltage law, you should know the sign conventions for how do we take the positive sign and negative sign while solving the any electric circuit, and then we can solve the examples related to the Kirchhoff voltage law and Kirchhoff current law. We can use the relationships which we have already derived in the case of inductor, capacitor and the resistance, the voltage current relationship, and using the Kirchhoff's law and voltage law and current law, we can find the current and voltage through any element. So these laws are used for finding the current and voltage. So dear students, we have discussed the preliminary part of the circuit theory, like the what is circuit, what is network. We have derived the relationship voltage and current for the case of circuit elements, resistance, inductance and the capacitance. We have studied what is this resistance, what is inductance, what is the significance of the capacitor, and what is the current voltage relationship in the case of the capacitor. We have seen what is the current source, what is the voltage source, and how do we represent the current source and the voltage source, ideal current source, ideal voltage source. How do we differentiate the voltage source, ideal voltage source with the practical voltage source. We have seen some examples related on this, and the next time we will study more on this topic. Thank you.